this lesson, I plan to introduce you to the Cartesian plane. The Cartesian plane is formed by starting off with two copies of the real number set. I want you to remember that the set of real numbers is just a set that contains every single number you've ever encountered. Now, in a previous lesson, you've been introduced to the Cartesian product, and I'd like to give you a brief reminder of what it is. Imagine starting off with two sets, which we'll call A and B. The Cartesian product of A and B is going to take every single possible coordinate where an element of A appears first and an element of B appears second. So therefore, we'll say that A times B is a new set, and it's made by taking elements from A first and then taking elements from B. So for example, one of the elements is this element AP, where we take the A from this set and then the P from this set. Another element is this BQ, where we take a B from the first set and then a Q from the second set. So therefore, we say that the Cartesian product contains every possible pair, where the first element is taken from the first set and the second element is taken from the second set. Now, it turns out that the Cartesian plane is just what you'd get when you take the Cartesian product of the real numbers with themselves. Now, one thing I want you to understand is that the real number sets are actually infinite sets, because there are an infinite number of possible numbers that you could have in each set. Now, the new set we're forming is going to be called R squared, and the reason we call it R squared is because it reminds us a little bit of the process of multiplying a number by itself. But in this case, you're multiplying a set by itself, and therefore it's kind of like you're squaring the set. Now, I want you to remember that the Cartesian product writes down every single possible pair, where the first element appears in the first set and the second element appears in the second set. So therefore, R squared is also going to be a set that contains a whole bunch of pairs, but it's going to contain every possible pair of numbers. So, for example, one possible pair of numbers is the pair 3, 2, where you took the 3 from the first set and the 2 from the second set. Another possible pair is the pair -7, 4, where -7 is taken from the first set and 4 is taken from the second set. Now, as we said, order is always important when you're taking the Cartesian product. We assume that the first number comes from the first set and the second number comes from the second set. So therefore, -7, 4 is different to 4 minus 7. Now, as you can imagine, there are many more pairs of real numbers. So let me go ahead and just fill out the set with just a few different examples. Now, in this set, there are some numbers that you probably do recognize and some numbers that you probably don't. For example, -1, 1, I think most of you would know. 0, 0 is a simple example. But then you've got the number pi e. Some of you may have seen the number pi before, but maybe the number e is new to you. But both of them are numbers and both of them have values, so they definitely belong in the set R squared. We also have pairs of surds like √2 minus √3, and pairs of rational numbers like 2.14 and 7 on 2. Now, as you already know, the real numbers form an infinite set, and therefore every possible pair of real numbers is also going to be an infinite set. So there's no way we could list out everything in this set, but we can just list out a few just to get a feel for them. So therefore, I'm going to say that the Cartesian plane is just what you'd get when you take the Cartesian product of the real numbers with itself. And if you do that, you're going to get every possible pair of real numbers. Now, it is not an exaggeration to say that the Cartesian plane is actually one of the most important problem-solving tools you're ever going to learn. By using the Cartesian plane, you're going to be able to turn a complicated problem into one that you can usually just see the answer to. But you might not see how something like this is actually going to be useful. But the reason it's useful is because of all the ways we can visualize the Cartesian plane. Now, one of the simplest ways to actually visualize the Cartesian plane also turns out to be one of the most useful. Remember that you can draw the real number line as a number line. Well, if you have two number lines, we might as well just draw two number lines. Now, I've randomly chosen to make the number lines go from -5 to 5, but they can really go from any number you like up to any number you like. But to help distinguish between these two different number lines, I'm going to label this one Rx, and I'm going to label this one Ry. Now, as we said, R squared contains every possible pair of numbers, right? So I want you to imagine that Rx is going to contain the first number in your list, and Ry is going to contain the second number. So let's choose a random value for Rx and a random value for Ry. Now, most of the time, people will call this value the x value, because it's the value on the first number line, which we called Rx. And then similarly, this value over here will be called the y value, because it's the value on Ry. Now, as you can see, the value on Rx is just -1, -2, and the value on Ry is just 1, 2, 3. So that means we have the pair of points -2, 3. Now, just to show that these 2 points are actually linked to each other, I've drawn this link over here to really emphasize that they are linked. And by linking them, we get this coordinate -2, 3. Now, I want you to understand that if you were to actually change the order of these two and actually get the point 3 - 2, then you'd actually draw the string backwards, so it would look like this instead. So the whole idea is, as you move this top point around, you'd be changing just the first coordinate in this tuple. If you then tried moving the second point around, then you'd only be changing the second coordinate in this tuple. We can call this thing over here a coordinate, or we can call it a tuple, whichever you prefer. So therefore, the first way to visualize the Cartesian plane is by visualizing it with this pair of number lines. Now, just to clarify this, r times r is the same thing as r squared, so you can write r times r is equal to r squared as well, if you like. So if this is actually a useful way to visualize the Cartesian plane, why don't we do some examples together to see exactly what the visual looks like? So here we'd like to draw the points 2, 1, -3, 1, and -2, 4 directly onto this pair of number lines. So just to show you what would usually happen, instead of naming this Rx, I've just named it X. And instead of naming this Ry, I've just named it Y. Also, instead of laying the number lines flat, I've just stood them up, and that's perfectly okay as well. Now for the first point, which is 2, 1, the first number line is going to have the number 2 on it, and the second one is going to have the number 1. So let's just link them up first. Now the next point is -3, 1. And we'd say that X is -3 and Y is 1. So we're going to start by marking out -3, then marking out the same 1 that we had before. And we're going to link them as well. And as for the last point, we want to mark out the point -2, 4. So it's going to have an X coordinate of -2 and a Y coordinate of 4. So we mark that out as well and link them. Now the main benefit of this method also turns out to be its main drawback. This method is so simple that you just have to find the X coordinate and the Y coordinate, and you just link them right up. But if you're trying to show more than one point on the same diagram, I want you to see that it just gets really messy. Imagine adding like 10 more points, it would just be a complete jumbled mess. Despite the fact that this can become a little bit messy, the idea of linking some set of numbers to another set of numbers is actually an incredibly powerful way to solve many problems, as you're going to see when you study more mathematics. Despite this, however, there is actually another way to visualize r squared that, when it was invented, was totally revolutionary. Between the 15th and 16th century, a French philosopher known as René Descartes came up with a really clever way to actually visualize this set, r squared. And the way he said to do this was to take these two sets and to redraw them so that they're actually perpendicular to each other, as I'm about to show you. Now initially, moving this axis here and then moving this axis so it's vertical might not seem like such a big deal. But historically, it was actually a huge deal. To show you why, let me try drawing the same point over here, -2, 3. Well, -2 would just end up over here, and 3 would just be 1, 2, 3 over here, right? So you've just got these 2 points over here, and that's not so crazy. Now, if this is where we stop, then nobody would really ever bother to do this. It looks more complicated after all. But the next step is actually really clever. We drop a vertical line from the first point, and then we drop a horizontal line from the second point. And then the point we actually end up drawing ends up being this point over here where these two lines intersect. So therefore, to indicate the point minus 2, 3, instead of drawing these 2 points, we just draw this one point over here. Now initially, I think you can agree that this seems more complicated than just drawing out the points directly, but it has one really big advantage. The idea is that every single point on the Cartesian plane ends up mapping to a different value for x and y. Every single one goes to a different pair of x and y. And therefore, instead of visualizing r squared like this, you can think of r squared as this picture over here. Every single point on this plane is going to be a point in r squared, and no point ever appears twice. Just to show you that no point ever appears twice, let's take a bunch of points like 1, 4 and 4, 1. So the point 1, 4 has an x-coordinate of 1 and a y-coordinate of 4. But then the point 4, 1 has an x-coordinate of 4 and a y-coordinate of 1, so therefore they join up here. So as you can see, for the point 4, 1, the x part is 4 and the y part is 1. But for the part 1, 4, the x part is 1 and the y part is actually 4. So despite the fact that they're very similar coordinates, I want you to see that they map to completely different places on the Cartesian plane. This method is actually genius because every point in r squared requires 2 numbers. So we use the fact that we have a 2-dimensional surface to represent every single pair of numbers, where we use the first dimension for the first number and the second dimension for the second number. Or in other words, the first dimension is just the x-axis and the second dimension is just the y-axis. So we use x for the first number and y for the second number. Now, to give you another way to think about this, I want you to imagine that I picked some random point on this Cartesian plane. Given a random point on the Cartesian plane, like this one over here, I always imagine having a really bright light shining on this point from the top. I want you to imagine that this is almost like a ball, and if we turn on this light, it's going to cast a shadow of the ball directly down on the x-axis. If you imagine the shadow cast by this ball onto the x-axis, the center of the shadow is actually going to be the x-coordinate of this ball on the x-axis. If I'm comparing this to the first visualization I gave you, you can think of this point almost as the point where we hit the first axis on our visualization. So therefore, this is going to be the x-coordinate. To give you an interesting way to visualize this, I want you to imagine that you're actually standing up here and looking down. If you do that, you'd just see the yellow ball, and you'd see its position on the x-axis, just as we see over here. So I guess at this point, we should get rid of this light and figure out what happens on the y-axis as well. So this time we've brought in a light from the right, and let's go ahead and turn it on and see where it hits the y-axis. This time, the center of the shadow actually lands on this point over here. Now for starters, I want you to imagine taking this point and moving it forward and backwards. If you do that, the shadow on the y-axis is not going to change at all. But if you move the point up and then down, you would actually see the shadow move up and down as well. However, if you did move the point left and then right, despite the fact that the y point won't change, the point on the x will actually move left and right as well. And for this reason, if you put this point in any single position, the shadows on the x and y axis are always going to be unique, and therefore the positions of the shadows determine the points. Now this point over here I'm going to call the y points, and if you imagine yourself standing out here and looking across, it would look exactly like this picture over here. You'd only see the point and you wouldn't be able to see its shadow. So now at this point we don't really need the light anymore, so we can get rid of it too. As we saw in our first visualization, the first point landed at -2, and that's going to be the first half of our coordinate. The second point landed at 3, and that's actually the second half of our coordinate. Now if the place where the first point landed is going to be called x, then that means that this -2 is the same thing as x. And if the second point lands at y, then this second point here is actually going to be y. So this coordinate is actually going to be xy. And in exactly the same way, we can say that this point over here is also going to be called the point xy. So to summarize this, instead of just visualizing r squared as a pair of number lines next to each other like this, we can instead visualize it as a pair of number lines that are actually rotated with respect to each other. So this big idea of rotating two number lines with respect to each other is called the Cartesian plane. So this whole thing is the Cartesian plane, and it's really just a useful way to visualize the set r squared. So now that you're familiar with this Cartesian plane here, let's actually go ahead and graph the exact same points that we graphed in the previous example on the Cartesian plane, and we'll see how it's different. Okay, so we want to draw these exact same 3 points on this xy axis down here. Remember, the axis moving horizontally is x, and the one that's vertical is called y. Now for this first point over here, which is 2, 1, we start by choosing x to be 2, and then y is going to have to be 1, so that means it's over here. Joining them horizontally puts the point right here. Now for the next point, we're looking for the point minus 3, 1. So the x-coordinate is minus 3, and the y-coordinate is just 1 again. Drawing the horizontal and vertical lines tells us that the main point is over here. Now finally, this point over here is minus 2, 4. So its x-coordinate is minus 2, and the y-coordinate is 4. Drawing in the lines shows us that this new point is over here. Now in a funny turn here, I want you to notice that these 3 points together actually draw out the shape of a triangle. And this is definitely not something you could have seen in this first diagram on the left. And this brings us to the biggest reason why we would bother to learn this method over here. When we just draw points on a pair of xy axes, you're missing the geometry. You can't actually see what's going on. But when you draw things on the Cartesian plane, patterns end up revealing themselves that would have been almost impossible to pick up on the original pair of crossed axes. But don't take this to mean that this picture is always better than this picture. It's absolutely not. Depending on the problem you're trying to solve, this picture may be more useful, or this picture may be more useful. It really depends on the problem that you're facing. But at this point, I think we've just about completed the example that I wanted to show you. So now I'm going to end this part with a caution. I want you to realize that these two visualizations are just tools, and you should always use the right tool for the right job. Don't always force yourself to think in terms of this, and don't always force yourself to think in terms of this. Despite this, most of the early problems in mathematics are perfectly well solved by either of these two methods, and in fact you're going to actually see this method quite a bit more when you're starting out. But at this point, I'd just like to summarize this lesson. In this lesson, we talked about the Cartesian plane. We said that you can form the Cartesian plane by taking the Cartesian product of the real numbers with themselves. And this will create a whole bunch of tuples or coordinates that contain every possible pair of real numbers. The majority of this lesson centered around different ways that we could visualize the Cartesian plane. Because we form the Cartesian plane by taking the Cartesian product of the real numbers with themselves, we usually call the Cartesian plane r squared. The first visual draws the first set as a number line and the second set as another number line. And then we show coordinates by choosing the x-coordinate and the y-coordinate separately and connecting them with a string. The whole idea is that you can independently move the first point around from the second point, and therefore every possible string represents a different coordinate. We said that this is a really useful way for solving a lot of problems, but the trouble is that if you try to draw lots of strings at the same time, it can get very, very crowded. So after this, we came up with a different visualization, which is by far going to be the most common one you're going to see, at least while you're starting out. In this visual, we imagine that we have a two-dimensional space that we can move around, and we place a point somewhere inside that two-dimensional space. The x-coordinate is found by casting a shadow from this point down to the x-axis, and the y-coordinate is found by casting a shadow to the y-axis. And then the whole idea is that as we move this point around the Cartesian plane, we'll see that the shadows are actually going to move around along the x and y-axis separately. Now initially, it seems like this method is much better than this method, because all of the different points map to different places in the Cartesian plane. However, as you're going to see throughout your studies of mathematics, Both of these different methods are useful for different situations. Sometimes this one's going to be easier, and other times this one's going to be easier. One of the main advantages of using this method over here is that if you draw more than one point, you can actually end up drawing geometrical shapes in the Cartesian plane, and that's not going to be something you can easily see with this method. However, in a follow-up lesson to this one, I'm going to talk about the three-dimensional Cartesian space, which you can form by taking the Cartesian product of R with itself 3 times. And in that lesson, you'll quickly start to see that this method actually tends to work a little bit better as we move on to higher and higher dimensions, whereas this one has a really big fatal flaw that I'll talk about in that lesson. So at this point, I think you've been sufficiently introduced to the Cartesian plane. So I hope you'll join me for the next lesson, where we'll talk about the three-dimensional version of this Cartesian plane, and we'll talk about how we can generalize it to even higher dimensions. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.